Lindfors Lindqvist from the School of Mechanical and Mechatronic Engineering at the University of Technology, Sydney, my previous uni. So Anna and I actually, we started our PhD roughly at the same time at UTS. So I have known her for many years. So throughout her career, she has been an outstanding engineer and researcher for both. So her research spans from vehicle dynamics and also control, transport system, and also the automation, and more recently renewable technologies as well. So during her PhD, Anna played a leading role in Australian technology network solar car projects. And also she has worked across academia, industry, government, and solving real world engineering problems. So we are very fortunate to have her with us today because Sydney is with 3 hours time difference than in Perth. So we appreciate that she can make it for this talk. So please join me in welcoming Dr. Anna for this talk. Thank you. We can start now, Anna.
Thank you, Lan. Unfortunately, I only have one screen, so let me do some of this admin stuff, and I'll just double check if you can see my screen. Hopefully you can.
Yeah, we can see the screen.
Oh, brilliant. All right, well, thank you for the introduction. And like Lan mentioned, we've known each other for a while. I started my PhD 2018 and have since obviously finished, worked in industry, come back to UTS, and also been promoted to senior lecturer. So I've done quite a quick career trajectory. So hopefully I'll give you some background on how I got there. Hopefully it lets me actually move stuff. There we go. So I guess where I'm going to start is really the
I think, Anna, you muted suddenly.
Ooh, okay, what about now? Am I back?
Now, yeah, you're back. Sorry to interrupt.
No, that's all good. Thank you. I don't know how much you captured, but this was the topic of my PhD. Can you still hear me?
Yeah, we can hear you clearly.
Okay, brilliant. Thank you. And actually, when I did my PhD, or sort of at the end of my PhD, I received the IEEE VTS Student Award. First time I got the second runner-up, and then the second time I applied, I won the award as well. So I've received 2 acknowledgements from IEEE VTS community, which has been quite lovely. So as part of my role, I was the team manager of the solar car team. So it made up out of 5 universities. So we had UTS, QUT, UniSA, Curtin, and RMIT. So despite being a student, I sort of worked both with the academics and some of our outreach people to combine and collaborate across all these universities. So if you think about it, if you go to Europe, they would build a car in the same city. We try to build something that's as big as Europe or larger than Europe, communicating with Perth, so Curtin, being so far away, and actually designing and building a car collaboratively. And the car did work. So this is a video. I'm not going to play it now, but if you type in ATN Solar Car Team, you can see it on YouTube. So we had some good achievements with the car. It was the fastest cruiser class car. So for the Bridgestone World Solar Challenge, essentially people design vehicles that run on solar power. And they have 2 classes. You have cruiser class, which is more like your conventional vehicle. It's sort of to sell new technology into the market. Or you have oh, I forgot what the other class is called now, but essentially they're the ones that look more like a spaceship, and they are competing like the fastest car on the road from Darwin to Adelaide. So we were more in the comfort class, if you want to call it that. But we had the lightest cruiser class, so we used resin-infused carbon for our chassis, and it was quite an interesting design, and also the design process of the vehicle itself. So it was a nice engagement between students and academics, industry, different researchers, media and government, and it was quite a great time just working with the students. So if you consider that my research was in the vehicle dynamics and the control of it, when I started, we didn't even have a car. So a lot of my work actually went into also building the car. So how does this fit in with research? Well, there's quite a few trends, mainly obviously environmental, social and government demands on having more sustainable transportation, but also things like safety and assistive control. So a lot of our modern vehicles, they're obviously quite well connected and safer than our traditional vehicles that were more manual handling and sort of human interface required. So one of the things that is really important in this case, especially when it comes to efficiency, is the reduction of weight. So the lighter something is, the less power it's going to take for it to drive. For the solar car, we had a very interesting curb to load weight ratio. So we think, yes, let's design lighter cars, but how does that impact internal parameters? So the change in load to curb weight, so empty weight versus when we start loading things in there, like people, luggage, whatever it might be. For a car that's only 282 was the design weight, but ended up being 346 kilos. But still the same sort of wheelbase and track as a normal car. Parameters change quite a lot. And that becomes a problem when we want to embed control. So for normal vehicle driver intent, I'll probably just skip over this quite quickly. But essentially, we want to make sure that we have the side steering ability of a vehicle. And when internal parameters change, the ability to steer will also change. So using assistive yaw moment, so direct yaw moment control, was sort of the solution that we were looking for, particularly in the case of the solar car, because it had two in-wheel rear motors. So essentially, you can adjust the torque between the motors to have an assistive yaw for more stable handling on the road. And this has been done in many ways. Your normal traditional differentials do that, sort of. But then you also have your braking or in-wheel motors to help you with that. So I sort of skipped ahead a little bit. So we did use the in-wheel motors. So these were the particular Moran motors that we used, which were designed for the solar car. But there's obviously other types of motors available as well. So the objectives was to identify the solar car dynamics. So we needed to build the vehicle to figure that out. Finalize and, ensure that the general stable handling was robust enough when we had load variation, and also to verify if the control strategy was safe to implement. So the method that I used was just the V-based model design, so model-based design approach, going through the whole V model. For the modeling, I used Siemens Amazon, where they have a multi-degree of freedom vehicle model available, which was embedded with MATLAB Simulink in order to actually develop the control. So doing a software in a loop, and then integrating it to the car. So the next step was hardware in a loop, using the DSpace micro order box, and then connecting that micro order box into the actual CAN network of the vehicle to do some real testing was the plan. So this was just the 15 degree of freedom model that we used in the simulation process. And essentially, we had a driver interpreter, which was just looking up the steering angle and the velocity, and then feeding that into the closed loop control with various observers. So I had the side slip observer, which detects slip when the vehicles are driving, but we also had an additional observer. I'll touch on it a little bit later. So normal vehicle dynamics, and again, I don't want to go into too much depth because it might bore some of you, but quite often when we want to have a stable, a reference model for our control design, a common one for vehicles is something called the bicycle model, which just translate it in to more simplistic dynamics where you can look at the over and understeer as well. Then we had the driver interpreter, which is what we used to look at the side handling. So whether we wanted to have a semi-neutral steer or over or understeering path. It's probably not what I was supposed to say. I do apologize. My brain is a little bit foggy at this point. So we also had the side slip observer, which was a model-based observer, which is also based on the bicycle model. There's also a kinematic-based observer, and in the process, I actually used both of them. So one worked better for the simulation part, and one worked better for real-life testing, obviously. So throughout developing the control concepts, we started out quite simple, or I started out quite simple, just a simple PI control. Then designing a sliding mode control for the vehicle, and then lastly a model predictive control. So going from simple to slightly more advanced. The model predictive control is pretty reasonable, like it predicts the future, if you want to say that, for each sampling, but it is a little bit heavier on the computational side when you implement it. Also had the torque allocator. In this case, we just split the side torque across the two wheels evenly, which was lovely. In the first simulations, we just did a very simple PI control to check the difference between an uncontrolled solar vehicle, more so to compare the fact that when you have a really light vehicle, it does not follow the path as good as something that's your standard size vehicle. So this purple graph here, or purple line on the chart here is the solar car in this case. Whereas when you have a normal vehicle, which is the blue one here, essentially handles pretty much as well as as a controlled solar vehicle. So the weight does matter quite a lot, especially when we reach high speeds. So the other thing we looked at was the load sensitivity. So again, the curb to load weight ratio, and this is where things started moving around, so the internal parameters. And for the solar car, we had some extreme cases, which I pointed out here, and it included the mass of, I think this case is the 1.2, so driver and passenger, the last one here. Driver, passenger, and then we had driver, passenger, and luggage. So it does change quite a bit. The main thing we found was there are some issues, particularly with the cases where the largest inertial change is happening, where the uncontrolled vehicle sort of does a phase shift, which is quite normal. Whereas heavier vehicles have lower yaw rate, and when we only update the mass sorry, in simulations, we do get a larger yaw rate. So something that we also found was that in some literature, people only update the overall mass for the simulation model instead of also updating the parameters. So they sort of miss out on the fact that they can get this phase shift. These were some of the results from the sliding mode control for the parametric changes. So essentially, we did see the phase shift still, but the sliding mode control was robust enough to actually handling it. And hopefully it's not too noisy. There was a lower error with some of the masses. Sorry, just some things happening in the background here. So essentially what we found, or the real finding, was that incorrect assumptions of a real vehicle versus simulation can actually impact the response of the control, which is why sometimes the simulation papers, or when we state that a control is so and so better in simulation, it won't necessarily reflect what happens in real life. So we also did control performance comparison between the sliding mode control and a PI. I'll just skip forward to the interesting parts, which is we had to embed this as software in the loop. So all these ones were all simulation results, but we did embed this in a software in a loop. So essentially, we wanted to make sure that when the control is implemented, it can also respond in a similar manner in real life. So we had the Siemens, we linked it with the MATLAB Simlink, as well as the DSpace micro order box. So essentially the control was then transferred to the micro order box for this particular case, and we could then test it with the vehicle still in Siemens. So that's what we called software in a loop. We also had wireless communication to the vehicle. I did add this slide today, and I'm not sure why it's actually in this part here, but essentially we could wirelessly monitor the solar car while we were doing any sort of testing, and that was the plan when we were going to implement the control into the vehicle itself. And we did have a real time setup as well, where we again used the DSpace micro order box alongside a laptop to enable and disable the control and embedded it into the CAN network of the solar car. So this was our general setup for the vehicle. However, we did have some limitations for this study. So remember, I started my PhD 2018, and it was very nicely situated around COVID. So when we had actually booked in track time for the car to go out on the track where we could enable the control, we had to cancel that. So the only testing we could do with the vehicle ended up being in a parking lot, so in a closed area at the back of Tech Lab at UTS. So if you've ever been there, it's quite a small space, so it didn't actually let us do some of the things we needed to do. So we couldn't actually get some of the actual parameters for the vehicle, mainly so the tire data. You need to drive in a circle to capture the data to estimate the parameters. So we had to estimate that from published research instead, and things like moment of inertia. So we did have some resource constraints as well, so people, funding, and test track. So wouldn't recommend again, but we did manage to get some of the parameters. Essentially, we just weighed the car and we ended up lifting up the rear just to try to find the Z axis as well. However, it did have to be estimated to some extent in the end. So finding the center of gravity, we did this with the empty vehicle, and we did this with the driver, and we also did this with a driver and passenger. So you can see how the position of the center of gravity changes depending on the loading scenario, essentially. So in order to get that position from the ground, you have to lift that rear up. We just stacked it in this way. The angle was quite small, which made it quite limited. And this was mainly because these were the resources we had access to at the time. We faced another problem. So again, I mentioned we drove in the back of a car park or loading dock, actually. They had these nice pillars, which were a little bit challenging to navigate around, but it was also on a bank angle. So the whole the driveway there is actually on a slope. So we had to adjust the side slip observer. So this was the side slip observer that was designed for the simulation. Whereas in this case, we also had to account for the gravity from the IMU when we capture the data to estimate how that changes. So you can see the impact of that steering, sorry, the slope of that driveway where things sort of went a little bit pear-shaped, but with the adjustments, that worked out just fine, which was great. So that's the red one with should have probably kept the coloring of the different tables the same, but the lateral acceleration, the red one has the gravity compensation, and for the side slip estimation, it's the black one. So you can see it does have quite a big impact on it. Then another issue, which was actually related to how the vehicle is built. The only place we could mount the steering angle was to this carbon fiber rod, and the only thing we could attach to it without actually damaging anything was a plastic bracket, and that ended up flexing when we drove on that bank angle because it was designed to be for flat driving, and that was what the suspension was designed for as well. So we had to also do a manual, and luckily that was just a manual offset that we had to adapt based on the direction of driving. So tire corner stiffness, that was the one we couldn't actually test for. So we had to estimate it based on published research instead, which is quite a large limitation. So we did have some real-time testing. I think this shows some of the driving that we had. So again, we couldn't go in excessive speeds. This car can go as your normal road vehicle at 100 plus kilometers an hour. But I think we only reached maybe 20 at most. And we could also monitor it while driving in the car, so driver and passenger, which was quite neat. And that was all through the interface with the DSpace micro order box. And this was some of the results for the testing. This has been published. You could, I don't think I put the actual papers at the end of this slide deck, but you can just find it off my Google Scholar if you want to have a look at them. But essentially, we tried it for the different scenarios. One of the things that we made sure to record as well was the tire pressure. So that had an impact as well. And we can see that we did get improvements based on the control implementation. So these were just the yaw rate for the different vehicles, just a raw one, side slip estimation error, which also did have a little bit of a drift, and the corrective torque depending on the different controllers. So we did do a model validation as well, comparing with the simulation. And then we also evaluated the safety of implementation. Now, one important note is that the results never had the control enabled, so it worked as a passive control. So all the results that we captured don't have a closed loop effect. So that's why we ended up having to do a validation back into the software again. And the reason for that was basically the space that we had available. We just couldn't embed it while we were driving back there. So it's mainly an open loop case. It would be nice to be able to enable it. Unfortunately, the vehicle is now with RMIT, I believe, and we've removed all the testing since. So this would have been, again, 2021 that this was captured, so quite a few years ago now. These were some of the publication at the time of me creating this particular presentation. There should be an additional one, a journal paper related to the comparison of the controls as well. That was published after my completion of my PhD. And that's pretty much it for my PhD. So after my PhD, I decided to leave, or rather I submitted my thesis when there was still COVID lockdowns, and my then supervisor got me involved with still working at UTS, so got me involved with designing some subjects. So I was working with UTS designing subjects when they were doing a curriculum change, and ended up working with the faculty team on these sort of developments. Now, my supervisor left UTS and joined Transport for New South Wales. And after a bit, he actually asked me if I wanted to come join the team. So I didn't technically leave UTS because on a casual basis, I was still working for them, assisting with the subject development. So whilst working at Transport in the Fleet Innovation and Technology Projects team, I was still very much involved with UTS as well. So this takes us away from, I guess, research or the traditional research and more into like an R&D sort of environment. If you're based in Sydney, you might have gone past the airport where they changed the lanes in the morning. This orange trailer looking thing is actually the equipment that changes the lane for them. And we did a big update and converted that to an electrical one, which is now working. It's been built and out on the road somewhere. And one of the other projects I was part of leading was working with XR Solutions with fleet inspectors. So these guys go out and essentially inspect vehicles for Transport for New South Wales. So if they're going to do work for Transport, they need to have approved vehicles. And this was just a trial to see, can we do that hands-free, essentially going in and check. And similar, this project the team works with projects that are building custom plant equipment or vehicles. So similar to this trailer, also build other things such as like a cone truck. So essentially placing traffic cones or picking up traffic cones whilst driving. So they sort of dabble in a lot of different areas where it comes to transport, mainly for automation and safety. But at the time of me joining, also worked on a big net zero emission transition plan, which I was involved with. And the other big thing I was involved with was looking into condition monitoring for bolts, for fans inside of tunnels, because that's currently something they inspect. Is there a way to use IoT to monitoring equipment that's difficult to access? And then one of the other big projects that I was working on for a while was scoping out a project related to repairing potholes in a quicker and more automated way without having people out on the road, essentially filling them in. And I was offered to stay on with this team, but at the same time, I was an international student, even as a PhD. So I did my undergraduates at UTS as an international student. I did my PhD UTS as an international student. And when I left my PhD, I was still very much not an Australian resident. So it became a little bit tricky. And as much as I would have loved to accept an offer at transport at the time, I was very much tied into my visa as well. And UTS actually came back and offered me a role as a lecturer. So because I kept working with the curriculum development and education, I still had a big part in there, and did quite a lot of work that's been recognised. So it was also nice when I got the offer. Luckily for me, I ended up getting the old innovation visa. So I actually became a resident quite closely after accepting the role at UTS. So coming back to UTS, I run a big subject. We have 300 students, and it's we call it a studio subject. Students build and design little robots that they compete against each other for the Warm and Design a Build challenge. And I use something called formative sprints. So essentially, students are very much required to work like they're in industry, like they have to take ownership of their work. They are sort of the expert, and we're there to advise them when they need it, but they should be the driver of their projects. So as part of coming back to UTS, which I got my PhD technically approved 2022, I then got my offer from UTS 2022 December. So already in 2023, I got an early career teaching award. The year after, I got a citation for outsetting early career contribution to engineering education from A Square E Square. So the Australasian Association for Engineering Education would highly recommend to join that community and go to the conference if you haven't been, because it's just a really lovely space and place to meet other people that work at universities. They do research and they do teaching and learning as well. So as much as I'm passionate about my technical research, I do really enjoy my educational research side as well. And that's what's really helped me advance in my career as well. And then I guess more recently, because we only found out this year in March, was the 2025 AAUT citation for outstanding contribution to student learning as well. And that's the national award from Australian universities, which is quite prestigious. Now, still being at UTS, I do dabble a lot in the educational research side, but I haven't completely dropped my technical field either. So I mainly still work with vehicles, even though a lot of my work is into mechanical design. But most recently, we just finalized a project with a company on renewable diesel and emission testing, which I was the project lead of. And the nice part with this was that during the process of doing this project, we managed to commission a dyno, so this blue thing you see at the bottom, indoor driving condition basically for a vehicle. We managed to commission that at UTS Tech Lab. It was decommissioned for quite some time. And this test cell has also been approved by the Department of Infrastructure for vehicle emission and energy consumption testing. And it's sort of like a joint facility of the capability across UTS and Swinburne. So I don't want to take any acknowledgement of this happening. So this is very much to this guy here on the right, Nick Soravsky from UTS, as well as their colleagues from Swinburne that organised this. I currently have a PhD student coming on board as I'm going on leave, unfortunately, that will keep doing some work that's been done on bus vibration. and essentially having more safe conditions for those with injuries or elderly or really anyone if you've been on a bus, looking at the impact of jerk and comfort in buses. That's pretty much it for me. I didn't want to take up all the time, so hopefully it will leave us some time for questions.
Thank you, Anna, for the wonderful talk. Is there any questions from the audience? Now is the time for Q&A. Okay, we have
Hi,
Shake.
Len. Yeah.
Hi.
Thank you very much, Anna. That's a very impressive talk. Like I like what you have done, and actually I commend to, what you have done in the industry and at the university. I just have a question on the observer part. You have mentioned that you have used two different model-based observers. Just wanted to know which one was good for experimentation and which one worked well with the simulation part. Yeah.
Okay, I'm just gonna have to go back into my slide deck, see where I had it. So before Lan invited me, I had not opened this work since I actually did my PhD.
Totally understand. I do the same. It's been a while since I saw my PhD thesis.
Yeah, that's it. You sort of want to get it over and done with almost. So it was for the side slip observer or estimation, I believe, maybe. Let me just go further back. Oh, yes. So we had the kinematic observer. I'll just share my screen.
Yes, sure.
Oh, no. There we go. This one. So for the model-based observer, we had this top one. So that's what we used for the simulation. So it was just based on the bicycle model.
Okay.
But because we had to estimate the tire data, we didn't actually have it. You can use the kinematic-based observer. So that was the plan to use for the roadside testing. Now, just remember, we never really enabled the control, so it was very much shown as a passive estimator.
Okay. Okay. So, like, did you try like Kalman filters or something like that?
I think we did at one point, but because of the live application, we never embedded it. So I think one of the constraints we had as well was that we were very much doing the testing and trying to do the reading of the data live. We never went to the stage, or rather, I ran out of time with my PhD to fully process the data with any sort of filtering. It would have been ideal to do at the end of the project, but I think this data was captured basically upon almost submission. So it was the fact that I wanted to have the real data collected for my PhD, not just the simulation, because that would have really, really limited the output. And in all honesty, the control and the testing was the last year of my PhD. Only. So it's like a year's worth of work only in that short time frame, mainly because we didn't have the actual vehicle. So a lot of the work before that was working with estimates of some of the parameters.
Thank you. Yeah, thank you, Len.
Thank you. Is there any other questions? You can just raise your hand. Hello, hi.
All right, thank you, Len. Thank you very much, Anna, for your excellent presentations regarding your PhD work and ongoing career. So I do have one concern because I have done similar research in my past few years regarding the slalom observer for estimating the side slip angle for the road vehicles. Yeah, so my first concern is you only verify the proposed slalom observer performance through the simulation, right? So have you done any like hardware in the loop verification? I know you haven't done any real-time experiments.
Yeah, so we did use it with the micro auto box.
Yeah.
But again, we couldn't use it as a closed loop circuit, right? Because if we had enabled that at the back, first of all, the risk assessment would have not been approved for us to do it at the back of that little driveway. That was sort of where the final outcome when I finished off was basically, this is what we would love to do.
Yep.
But that's the only stage we could get to at that point in time.
Okay. So what is the current, the research, the activities that have been carried out for your school in UTS? Are there any researchers doing the ongoing research focusing on this area? Or
it is very limited, I'm not going to lie. So a lot of the people that were experts in this field left UTS.
Yeah.
And a lot of the team that I worked with, they're actually no longer at UTS. So it's really just me that is still there. We do still have people from other parts of UTS, however, which I'm not necessarily strongly connected with, but I know they still do vehicle research as well. So if anyone's in this call, like, feel free to put your hand up and say it's me. But I know they were doing some on the sort of computer science side because they tend to do like a little bit more heavier control in terms of applying it and stuff. And then obviously I've also worked, so my co-supervisor was Ricardo Aguilera. So he's from School of Electrical. He will now be part of the new school as well, who's in the control area. And is taking care of our motorsports team at the moment.
Yeah, because I'm quite curious about once the slalom observer implementing the real vehicle, what is the performance compared to the hardware in the loop, in the simulation, or even pure simulation? Yeah.
I mean, it would have been an ideal platform.
Yeah.
It would have really been a nice platform to use. Unfortunately, after I wrapped up my testing, the car got shipped off to one of the other universities. I think, I mean, I'm not sure if Ricardo's in that area completely. He's more into battery research, but he might be a potential person in this field. We are trying to pick up some of our capabilities again, or rather, we do have the capabilities for other vehicle-related research, mainly in the dynamics and emission side of things, so performance-related.
Yeah.
So that's currently where we're heading and where we're aiming, so to speak.
Okay, good. Yeah. So any driving simulator in UTS at this moment?
I think they have one sitting with a different school, and they're using it for a different purpose.
Oh, okay.
So I know the
school. Okay.
Yeah, they're looking at I think motion sickness and things like that.
From different perspective rather than the vehicle dynamics.
Yeah.
Okay, no problem. Thank you, Anna.
Thank you.
Thank you. Hi. I do have two questions. I never got a chance to ask Anna. Bingo. The first question is, you did mention lots of simulation, right? So is there any difficulties when you apply the simulation result to the real car? It's like lesson learned from that.
I mean, with the simulation, it's always in an ideal environment. Everything looks very nice. And I think that's where a lot of the phase shifts that we saw when internal parameters change, if you don't account for those happening in a simulation model, the control actually responds different. So that was sort of the early research that we did as well, that quite often it can be overlooked in simulation to update all the different parameters. So what happens is that weight tends to be updated because it's just the simple assumption. But it's not always obvious if people update all the parameters that comes with this additional weight, or are they assuming that an increase in weight is just a point load which remains all your parameters, right? So in real life, that is not as simple as just a point load, but also the parameters do change in real life, right? So with the dynamics added, we do need to consider that it's not just a linear model anymore.
Yep. Another question is there any future plan about to like further develop the car in the crazy mode, like autonomous solar car as well?
I'm sure the bridge, like I would recommend to look up the Bridgestone World Solar Challenge. That's still very much running. They run every second year. We don't have much involvement with it anymore. So after people leaving UTS, we don't necessarily work extensively with it.
Thank you. We have further questions from Kai as well.
Yeah, yeah, I do have another question regarding the teaching, so engineering teaching. So I can see that Anna has received many awards from the teaching awards, citation. Yeah, that's the very great, the achievement. So would you mind sharing some of the experience or knowledge regarding the, or you can share with us some of the key parts from one of your awards in the engineering teaching part? Yeah.
Oh, okay. Yeah, they're quite
Thank you.
complex because I do a lot of things. So I like working with other people. I think that's my main thing. So working in isolation rarely gets you very far. So working with a lot of different people and collaborating tends to be very, very good for your career, but also that's what I enjoy. So I worked a lot with people from the faculty, but also externally. So if I saw someone on LinkedIn that I thought was like, oh, they're doing some really great stuff, I would reach out and be like, hello, I'm going to be in the area of where you are. Can I come by and have a look at how you guys do things? So I guess for the citations and the awards that I've received, it's more so about not just delivering for the sake of delivering teaching. So I know a lot of people are maybe not super keen on teaching. It can be quite admin heavy. It can be, it can be challenging at times, right? But I quite enjoy challenging students as well, and seeing teaching more as the communication and having a very active learning space rather than just talk against some slides. I'm not so much for presenting slides and presentations. I like show and tell. So you could probably see I have a lot of images, and similar with the teaching. So we work in, the subject itself is quite interactive, but essentially students need to work with feedback, and it's a very feedback-rich environment. So they will go and deliver something. We don't actually give them marks or points for this. They get a performance level. So you're currently sitting at this level, then they come back and represent. Now I'm up here. We give them feedback again. Sometimes they've headed the right direction. Sometimes they need a bit of help to get where they need to be. And at the end of the subject, they get one singular grade based on their overall achievement. So try to look at the teaching as if they were in the workplace as well. So it's not just about throwing information, it's about trying to tell students this is what you can do with the information I give you. Yeah, I do have quite a lot of like the workshops in teaching and learning. So if you want to look them up, you can also I'm happy to share them. A lot of it has to do with reflections and using AI in education and things like that.
No problem. Thank you. Thank you very much.
I think I definitely need that. Thank you, Hai, thank you, Anna. We have another question from Nash. Hello, Ali.
Hello. Thank you, Anna, for your kind presentation. I have one question regarding your research, which is related with AI. How do you see AI and data-driven methods integrating with traditional engineering disciplines? And since you have done your PhD in 2000 from 2018, do you think if we talk about AI, how uh, rapidly it has changed, what this AI can impact with this research?
Oh, I think a lot of things would have been done a lot quicker because I think, or at least my time spent on my PhD, I spent a lot of time talking to people, communicating with people, writing a lot of emails and arguments to people. That is obviously one of the more obvious places where you can use AI without it ethically impacting anything you do, as long as you don't share any personal or project details. But in terms of double checking things like control, I'm also a very sporadic worker. I work on probably 10 things at the same time, which also makes it possible for me to do a lot of tiny mistakes. So just checking on certain things, like when you do your variables and whatnot, be like, is this accurate? Yeah, I'm not sure how to answer this question concisely because it depends on where you use AI, or rather generative AI in your work. Because I guess it's slightly different than just using machine learning as traditionally used. There's so much information available. One of the places where we use it for the research project that I have worked on, because I do have quite a few publications with the AI in engineering education, is the ones that embed with literature searches. It's quite helpful in finding good literature, but always making sure you validate back if it's actually accurate, the summaries you get. It's still a little bit funky and wonky, I find, but it is quite good at finding those particular references that you sometimes need. Because I think I spent a lot of times searching for papers that aligned with what I needed at the time. And anyone doing literature reviews, the traditional way was quite tedious. You had to bank all your references, whereas now you can actually just have a written note with the references instead of using like Mendeley or whatever it might be. And obviously, if you're using LaTeX, I think if GenAI was available back then, it would have been quite helpful in editing the LaTeX structures that you need for some of your papers.
Yes, sure. Thank you. But do you think is there any limitation which we can reduce with today's AI with your work? Any risk factor or limitation? Not in the writing side, in practical side.
In the practical side, well, I am quite cautious about what you put into AI. So if you work with a project that has sensitive information, you're also limited to the extent that you should be using AI in your work, right?
Thank you.
But in terms of practical things, if you want to double check the more basic things, so I'm still a hand counter, like the more simple the maths, the more I need support, almost like a calculator. But for like basic planning of experiments and things like that, it can definitely be quite useful.
Yes. Thank you, Anna. Thank you.
Thank you, Ali. Is there any further questions? So if there are no further questions, please join me in thanking Anna once again for this wonderful talk. Yeah. And also thank you, Professor Hai Wang, for arranging all this seminar. And I will see you again in Sydney, I think, very soon for RSS conference.
Oh, okay.
Yeah.
Thank you.
All right, thank you, Anna, for your time and effort for supporting our VTS WA chapter event. Thank you very much. Thank you.
Not
And
a
thanks,
problem.
Lan, for coordinating this event.
Thank you.
All right,
It's
so,
presently in Sydney, I think.
All right, so thanks everyone for joining today's event as well. So enjoy the rest of the day and enjoy. And I'm looking forward to seeing everyone in next month's event. Thank you.
Thank you.
Thank you, Anna.
Thank you.
Thank you.
Bye.
Thank you,
Bye,
sir.
Anna.
Thank you.
Bye-bye. Bye-bye, everyone.